welcome to my channel. Let's start with the part 3. In this, I would be covering ideal gas equations and important questions related to these. Now, in this case, as you know that the behavior of gases is dependent on pressure, volume and temperature. And now you can see that I have written one equation, that is PV equals to KT. Now in this case, the K is a Boltzmann constant. Now K varies with the number of molecules and Kb. Let's write the big K can be written as number of molecules times Kb. Now in this case the Kb is the Boltzmann constant, which has a value of 1.83 into 10 raised to power minus 23 joule Kelvin inverse. Now in this case the Kb, Boltzmann constant, for any gas is same. Let us see how they are same. So as you know, we can interchange the values of these. PV can be written as NKB first of all, NKBT. Now from this you can find the value of Kb. So Kb will be PV over NT. That means if I take two different gases, let us suppose that I am taking two different gases having different pressure, different volume, different number of molecules, different temperature, and we can take another gas that has P2, V2, N2, T2. It will be a constant. The ratio of PV over NT in both cases will be a constant equal to Boltzmann constant. It is known as Boltzmann constant Kb and its value is 1.83 into 10 raised to power minus 23 joule Kelvin inverse. Now let us move on to the Avogadro's hypothesis. So he gave one law. He actually established that in the case of 22.4 liter of gas, 22.4 liter of any gas at NTP, NTP means normal temperature pressure, is known to have contained the same number of molecules, that is 6.023 into 10 raised to power 23. So these many molecules will be there. So this was the Avogadro constant and it is represented by Na. So it is known that Na for any gas that is having the quantity of 22.4 liter, and it should be at normal temperature, that is 273 Kelvin, and it should be at normal pressure, that is 1 atmosphere. Then only this quantity is true. Now let's see how to obtain value under mu mole of gas. So as you know that mu is the number of molecules. It can be written as m over m naught. M here is the mass of the gas and m naught here is the molecular mass of the gas. So m, remember that m in this case is mass of the gas that contains n molecules, and m naught is the Avogadro constant. And similarly we can compare the Avogadro constant. So n will be the number of molecules and Avogadro constant will be Na. That's how we find number of molecules. So as you know that R can be written as NaKb. Na is the Avogadro constant and Kb is the Boltzmann constant. So the value for R is this. Now putting the value of R in PV RT. So PV can be replaced with NaKb T mu RT. Now, as you know that mu Na from this equation, mu Na will be equal to N. So I will replace mu Na with N. So PV N KB T. Now we have V here. So we can bring V down. So it will be P using cross multiplication. It will be N over V kBt. So now as you know that number of molecules over volume can be replaced by number of molecules, or you can say number of molecules per unit volume equal to number density of gas. So it can be written as P equals mu kBt. So this is another formula when we have mu mole of gas. So this can be written. Now, next thing is that if we take a mass density, let us consider that we have a mass density of rho. So mass density, as you know, can be written as rho equals m over v, or you can write the volume quantity as m over rho. Now, as you know that P is equal to mu RT over V. Now putting the value of V in this, mu RT over M over rho. Now in this case, as you know that M is from this equation. M will be equal to mu M naught. So let's put M value as mu M naught. Mu can be cut down with mu and you will be left with RT rho M naught. So these are some of the values under different conditions, like you can find in the case we have mu P equal to mu PV equal to mu RT. These are some of the conditions. Let us look here. So PV is equal to RT when we have 1 mole, or you can say 22.4 liter of gas. So this is the fixed quantity. Now for mu mole of gas, you need to just put mu here. For 1 molecule of gas, we have PV equal to RNA T, or you can write K equals RNA. So that's how you derive this. For n molecules of gas, you need to put NKT. For 1 gram of mass, you need to take R over M. And for n gram of mass, you just need to add, sorry, not add, times it with nRT. So that's about ideal gas equation. So let's start with some problems based on ideal gas equations. So let's have a look at problem 7. So a gas at 27 degrees Celsius has a volume V and pressure P. On heating, its pressure is doubled and volume becomes 3 times. The resulting temperature of the gas will be. So we need to find the new temperature in this case. So as you know from ideal gas equation, we have PV equals mu RT, and this can be written as T, as you know that T is dependent on P and V value. So I can write T2 over T1 equal to P2 V2 P1 V1. So this is what we obtained. And now it says that a gas at 27 degrees Celsius. The initial one has volume V and the pressure P. Now when we heat that, the pressure is doubled. So 2P1, this has been changed into 2P1, and the volume becomes 3 times, that is 3V1. So P1 and V1 gets cancelled out. You are left with 6. That is 2T over T1. Now T2 equals 6T1. Now T1 is in this case is 300. You have to change it in Kelvin, so it will be 300. 300 times 6 is 1800 Kelvin. Now if you want to change it into degrees Celsius, it will be 1527 degrees Celsius, C part. Let us move on to the next one. So a balloon contains 500 meter cube of helium at 27 degrees Celsius and 1 atmosphere pressure. The volume of the helium gas at -3 degrees Celsius temperature and 0.5 atmosphere pressure will be. So we need to find volume in this case. Again, we have two different quantities. So let us look at how V is dependent on T and P. So as you know, again, PV is equal to mu RT. So we need to find volume. So volume is dependent on R and T and P. R by T, R dot T over P and mu here. So mu is common to both. So it can be written as V2 over V1. Now the constant quantities can be cut down. So we just need T and P in this case. So T2 P2 it will be down and then times it with V1. V1 quantity is dependent on T1 and P1 will be at numerator. So T2 times P1 over P2 times T1. So let us change the values as per the question. So the T2 in this case is 27 degrees Celsius. It will be -3 degrees Celsius because we need to take the new one. So it will be 270. Need to change -3 degrees Celsius to Kelvin. So it will be 270. Then P2 in this case is 0.5 and T1 in this case is 300 and atmosphere pressure is 1. So let us solve this and you will get your answer as 9 over 5 when you solve this, V2 over V1. That means V2 is dependent on V1 by 9 over 5. So putting the value of V1, V1 in this case is given as 500. So V2 equals 9 over 5 into 500. So this will be 900 meter cube. So the right answer is C. Let us move on to problem 9. When volume of system is increased 2 times and temperature is decreased half of its initial temperature, then pressure becomes. So now we need to find the pressure change. So pressure is dependent on again we need to take care of T and V as mu and R is common. So P2 over P1 equals T2 over V2 times T1 over V1, reciprocal of it. Now as it is given that it has been decreased half of its initial temperature, that is T1 over 2 over V2. V2 has been changed to increased 2 times, that means 2V1 into V1 over T1. T1 gets cancelled out, V1 gets cancelled out. So P2 is equal to it will be at 1 by 4 because taking reciprocal of it you will get 1 by 4 of P1. So that means the right option is C, that is 1 by 4 times. The equation of state corresponding to 8 gram of oxygen is. So we need to find which is the right equation out of these four. So as 32 gram, as we have O2, that means the molecular mass will be 16 times 2, 32 gram. So 32 gram means 1 mole. Therefore, 8 gram of O2 means 1 by 4 mole. 1 by 4 mole. So that means mu is equal to 1 by 4 mole. Now, PV is equal to mu RT. So PV equal to 1 by 4 RT. So right option in this case is B. Now, the next question is 11th question is, a flask is filled with 13 grams of an ideal gas at 27 degrees Celsius and its temperature is raised to 52 degrees Celsius. The mass of the gas that has to be released to maintain the temperature of the gas in the flask at 52 degrees Celsius and the pressure remaining the same. Now, as you know that PV is directly proportional to mass of gas into temperature. Now, as you know that we have, say in this problem, pressure and volume remains constant. So we can write m1 dot T1 equal to m2 dot T2, which is constant here. Now, in this case, we can use cross multiplication and put all the values to get m2. We need to find the mass of second gas. So m1 in, or you can just simplify this first, m2 over m1 equal to T1 over T2, which is equal to 27 plus 273. The first one will be changed to Kelvin. Then 52 plus 273 again equal to m2 over m1. m2 is unknown to us. m1 in this case is 13 gram. Now solving this equation, we will get 300 over 325 equals m2 and 13 will be here, and after solving this you will get your answer as 12 gram. But in this case, as it says, the mass of the gas that has to be released to maintain the temperature of the gas in the flask at 52 degrees Celsius and the pressure remaining the same. That means this mass has been released out. So you have to subtract m1 and m2. So it will be 13 minus 12, which is 1 gram. The right option in this case is D. Now moving on to problem 12. Now in this case it says that air is filled at 60 degrees Celsius in a vessel of open mouth. The vessel is heated to a temperature T so that 1/4 part of air escapes. Assuming the volume of vessel remaining constant, the value of T is. So we need to find the value of T in this case. So let's do this again. T1 in this case is 60. So we need to convert this into Kelvin. So it will be 333 Kelvin. And M2 in this case will be the mass escaped. So M minus M over 4th. 1/4 part of air escapes. So that taking LCM, you will get 4 3m. Now, as you know, in this case again the pressure and volume of gas remains constant. Again we can make use of that equation, m1 T1 equal m2 T2. Now m1 in this case is m and T1 in this case is 333. m2 in this case is 3m over 4 into T2. T2 in this case is unknown to us. So let's find the value for same. So m and m gets cancelled out, and using cross multiplication we will get 444 Kelvin, or you can write it as 171 degree Celsius. The right option in this case is D. Let us move on to question number 13. So in this case, it says if the intermolecular forces vanish away, the volume occupied by the molecules contained in 4.5 kg water at standard temperature and pressure will be given by. So as you know, they are asking you to find V in this case, but for that we need to know what mu is. Mu is nothing but mass over molecular mass. So mass in this case is 4.5 and molecular mass of water is 18. I need to convert that into kg to find the. So after solving this, you will get mu as 250. That means number of moles per unit volume, or you can say number of molecules per unit volume, or you can say number density of gas. So it will be 250 in this case. Temperature in this case is 273 because it says that we have a standard temperature and pressure. That means pressure, standard pressure in this case is 10 raised to power 5 Newton over meter square. This is at STP. So PV equals mu RT. This is for ideal gas equation. So V will be mu RT over P. Now putting all values of mu, R and T and P, you will get your answer as 5.6 meter cube. So the right option in this is A part. Let us move on to problem number 14. It says the pressure P, volume V and temperature of a gas in the jar A and the other gas in the jar B at pressure 2P, volume V4 and temperature 2T, then the ratio of the number of molecules in the jar A and B will be. So as you know that PV equal to mu RT, but in this case we need to write in terms of number of molecules. So PV equals mu RT equals N over Na RT, converting mu. Now as you can see that N is dependent on PV and T. How? PV and T equals PV and T, sorry, N will be here and no N here. So PV over T equals N. Now in this case we need to compare two quantities, that is N1 over N2. So for the first one it will be P1, V1, T1 and V2 and T1 and T2 at the numerator. So in this case we have pressure, volume and temperature. So the first one is same, that is P. V is same for V1 and T2 is 2T, this one. Now P2 in this case will be 2P and V in this case is V4 and T in this case is same for the first one. So let us cancel out whatever we can. So we are left with 1 over 4 at the numerator, that means 4 over 1. That means N1 is equal to 4 times N2. So, or you can say 4:1 according to the answer. So that means D is the right option. Let us move on to problem number 15. So in this case, it says the expansion of an ideal gas of mass m at constant pressure P is given by the straight line D. Then the expansion of the same ideal gas of mass 2m at a pressure P2 is given by the straight line. Now, as you know that PV is directly proportional to m over T, or you can write it as V is directly proportional to m over P T. That means MP defines slope of the graph according to this question. As we have V over T, so it is directly proportional to mass over mass of the gas molecules and pressure. Now, for first condition, slope MP graph is D in this case. As you can see, here we have 5 different curves here, that is A, B, C, D and E. So we need to talk about D. So as you can see, for first condition, the slope is m over P. Now for second condition, slope will be 2m and P in this case will be P by 2 as it is given in the question. So 2m, m will be replaced by 2m and P will be replaced by P by 2. That means if I solve this, I will get the answer as 4mp. That means that slope becomes 4 times. So graph A is correct in this equation as it has 8 volume and the rest of the all are wrong. So that means A is the right option. Let us move on to problem number 16. So it says if the value of molar gas constant is 8.3 joule per mole Kelvin, the n specific gas constant for hydrogen in joule over mole Kelvin will be. So as you know, the specific gas constant is given by universal gas constant, that is R, and then we have molecular weight and represented by m. So we have R value, that is 8.3, molecular weight is 2 in this case, and so it will be 4.15 joule mole Kelvin. So this is the right option. A is the right option in this case. Let us move on to question number 17. So in this case, it is given that a gas in container A is in thermal equilibrium with another gas in container B. Both contain equal masses of two gases in the respective containers. Which of the following can be true? So as you know, if I consider the ideal gas equation, and we have two gases here, so I will name it as A and B. So PA, mu A equal to PB, VB Vb over mu b. As temperature of the container are equal, so therefore we can write this equation. So now in this case it is also said that mu is different for both the cases. According to this question, it says that mu is different. Why? Because mass of gases are equal, so number of moles will not be equal. So mu A is not equal to mu B. Now moving on to the next relation. So as you know that PA is equal to PB according to this equation, this given equation. And then if PA and PB is equal, that means they can be cancelled out. So you are left with VA mu A equal to VB mu B. Now that means VA is not equal to VB. If I say that VA is equal to VB, then what we are left with? Let us consider that VA is equal to VB in this equation, in the first equation. So you are left with PA over mu A equal to PB over mu B. Now PA over mu A or PA over mu A is equal to PB over mu B will not be equal to 0. Why? Because if I rewrite this, PA over PB is equal to mu A over mu B. It can't be equal to 1. Why? Because mu A is not equal to mu B or PA is not equal to PB. So that means PA is also not equal to PB. So what will be the condition in this case? So the right option in this case is either B or C. So it actually has two equations to answer to this question. So let's move on to the next one. Two identical glass bulbs are interconnected by a thin glass tube. A gas is filled in these bulbs at NTP. If one bulb is placed in ice and another bulb is placed in hot bath, then pressure of the gas becomes 1.5 times. The temperature of hot bath will be 100 degrees Celsius, 182 degrees Celsius, 256 degrees Celsius, 546 degrees Celsius. So now, as quantity of gas in these bubbles is constant, that means initial number of moles in both bulb and final number of moles are equal. That means let us consider that mu1 plus mu2 in the ice one is equal to mu1 plus mu2 in the hot bath. So let us apply the equation of ideal gas. So PVR, the first is 273 because it is at NTP. PVR 273 equal to 1.5 PV because it says that the pressure becomes 1.5. So I'm timing with time P with 1.5. So R 273, and for the last one it is not given for the hot bath for mu2. Now it will be 1.5 PV RT. Now solving this equation you will get 2 by 273. Why? Because PV and R will get cancelled out from all. Now here on the right hand side you are left with 1.5 over 273 plus 1.5 over T. Now when you solve this you will get your answer as T equal to 819 Kelvin, or you can write it as 546 degree Celsius. So that means the last option is the correct one. Thank you for watching this video. I will cover the kinetic energy topic in the next class. Thank you for watching this.